The Apollo 13 mission was arguably NASA's finest hours. Thanks to a deep understanding of orbital mechanics and satellite maneuvering, NASA was able to save the lives of 3 astronauts, including Colorado's own Jack Swigert. I'm Mark McLean, and today I'm doing my presentation on satellite orbits and maneuvers. The most basic part of orbits is Kepler's laws of motion, of planetary motion. The first law states that every planet orbits in an ellipse around the sun. The second law states that a line joining a planet and the sun sweeps out equal areas during equal intervals of time. So basically, area 1 and area 2 have the same area. Therefore, the time it takes for the planet to travel from here to here is the same as the time it takes a planet to travel from this point to this point. The third law is that the square of the orbital period is directly proportional to the cube of the semi-major axis of the orbit. So basically, the square of the time that it takes a planet to go from this point all the way around the orbit back to this point is directly proportional to the cube of half of the length of the ellipse. There are 6 orbital parameters: the orbit's size, shape, orientation, tilt, twist, and location. The orbit's size is the semi-major axis, which is half of the length of the orbit. The shape is the eccentricity, which is the orbit's width over the orbit's length. The orbit's tilt is the inclination, or the angle between the equatorial plane and the angle between the ascending orbital plane. The twist is the right ascension of the ascending node, which is the point from the reference direction, or first point of Aries, to the ascending node here. The orbit's orientation is the argument of perigee, which is the angle from the ascending node to the perigee, which is the closest point to Earth from the orbit. The satellite's location in the orbit is true anomaly, which is the angle from perigee to the satellite. In order to find that, you take the vector from perigee and from the satellite, and it is the angle between those 2 vectors. The satellite maneuvering, the most fuel efficient coplanar transfer is a Hohmann transfer. There are 2 types of Hohmann transfers: coplanar transfers and coapsidal transfers. Coplanar orbits are orbits in the same plane, and coapsidal orbits are orbits with the major axis aligned. There are also change in velocity orbits, change in velocity transfers. They are the instantaneous velocity, basically changing velocity to change the orbit. All orbital transfers are change in velocity. Now, here's an example of a satellite maneuver. So, the satellite starts in this low Earth orbit, or orbit 1. It then boosts at this point to reach the transfer orbit and come out here. But it doesn't have enough speed to stay in the geosynchronous orbit, so then it gets pulled back in and becomes this transfer orbit, which is an ellipse. In order to stay out in the geosynchronous orbit, it has to boost here in orbit 1 and then it must boost again once it reaches the right height. Once it boosts twice, it can then stay in the geosynchronous orbit. This is the math for it. Velocity 1 is how fast the satellite must go in this orbit, in this low Earth orbit. The satellite, while in this low Earth orbit, is traveling at 7.66 kilometers per second. At this point, it must then boost to add speed in order to reach out here. It adds 2.4 kilometers per second, and at that instant when it boosts, it is then at 10.06 kilometers per second. Once it comes out here and reaches this point over here, it is now traveling at 1.6 kilometers per second. It must then boost again to remain in the geosynchronous orbit. It has to add 1.46 kilometers per second, totaling a speed of 3.07 kilometers per second while remaining in this geosynchronous orbit. Thank you for watching.